Good morning, friends. Till now, we analyzed the amplifiers at the mid-band frequencies. Yes. So, today we'll analyze the amplifiers at the low frequencies. It's nothing but low frequency analysis of amplifiers or low frequency amplifiers. Yes. So, the analysis of amplifiers is common in both the frequencies, but here the effect of capacitors we need to consider here. Yes. So amplifiers are analyzed at low frequency by considering the effect of large capacitors. Amplifiers are analyzed at low frequencies by considering the effect of large capacitors. Yes. So in small signal amplifiers, we know we are operating in three frequencies. One is mid-band frequencies or mid frequencies. Another one is small frequency or low frequencies, and third one is higher frequencies. Yes, till now we analyzed the amplifiers at the mid-band frequencies. Yes, so in this case we are assumed the two types of capacitors, large capacitors and small capacitors. As large capacitors in sense it is in microfarad, and small capacitors are in sense in picofarad. Yes. So in mid-band frequency analysis, that we consider the large capacitors are short circuited. Yes. And small capacitors are open circuited. So while we are analyzing the amplifiers at the mid-band frequencies, till now we consider the larger capacitors are short circuited, that means which are in microfarad capacitance, and smaller capacitance are we consider as open circuited, which are in picofarad. Yes. In the low frequency analysis, we need to consider the effect of large capacitor. Yes. So effect must be considered here. Yes. And small capacitors which are in picofarad, again we are considering them as a open circuited. Yes. Coming to the high frequency, these large capacitors work as short circuited. Yes, why? Because reactance Xc equals to 1 by j omega c. Yes, so if frequency is high and capacitance is high, so that impedance or reactance offered by the capacitance is small. So in this case we can consider it as a short circuited. Yes, and coming to the small capacitors, we need to consider this effect. So effect of these small capacitors is considered. Effect is considered here. Yes. So till now we analyzed the amplifiers at small signal amplifiers at mid frequencies. Yes. And now we are going to analyze the amplifiers at low frequencies. In this case, we need to consider the effect of the large capacitors. We are not considering them as short circuited. Yes, here these small capacitors will offer the very high reactance at low frequency. Yes, so we can say small capacitors offers high reactance at low frequency. At low frequency. Hence, it can be taken as open circuited. Taken as open circuited. Yes. So Xc equals to 1 by j omega c. Here capacitance is small and frequencies are small. So that impedance or reactance offered by the capacitance is very high. That's why we are considering it is open circuited. Yes. And reactance of large capacitors. Reactance of large capacitors is neither too small nor too high at low frequencies. Low frequencies. Therefore, the effect is considered here. Therefore, effect is considered here. Yes. So, now we'll analyze the effect of coupling capacitors in the CE amplifiers at low frequencies. As we know, our RC coupled amplifier has 3 capacitors. Our RC coupled CE amplifier has 3 capacitors that are blocking capacitor, coupling capacitor, and bypass capacitor. Bypass capacitor. Yes. So in RC coupled CE amplifier has 3 capacitors. We know that is blocking capacitor, that means CB, and coupling capacitor CC, and bypass capacitor CE. Yes. To simplify the analysis, of effect of the any one of the capacitor, we need to ignore the remaining 2 capacitors. At a time, we can analyze the amplifier with 1 capacitor only. In this case, we are considering the remaining 2 are ignored. Yes. Finally, we can write the effect of all the 3 capacitors. Yes. So, to simplify the analysis, effect of one capacitor is considered at a time, and other 2 capacitors are ignored. That means short circuited. Yes. So to simplify the analysis, the effect of one capacitor at a time and other 2 are ignored. Yes, we are considering at a time only one capacitor. So now we will calculate the effect of coupling capacitor at low frequencies. Effect of coupling capacitor at low frequency. Yes. So we know that CE amplifier has RC coupled CE amplifier has three capacitors. One is CB and CC and CE. Yes. So we are considering that CB and CE are considered as short circuited. As short circuited. Yes. Then we can draw the circuit like this. As common emitter. So when CE is short circuited, the effect of RA is 0. As the effect of RA is 0. Now it is RC. Yes, and we are considering only one capacitor, coupling capacitor, that is CC. Now it is our RL. This is coupling capacitor. Yes, and this is V0. And here blocking capacitor CB is also short circuited. So here it is RB. This is source resistance RS. Here it is Vs. Yes. So this is our RC coupled CE amplifier, and we are assumed that CB and CE are short circuited. Why? Because we are calculating the effect of this coupling capacitor. When we are calculating the effect of coupling capacitor, the remaining capacitors must be short circuited. Yes, this is first step. Yes, we know replace the BJT with or transistor with approximate H parameter model, with approximate H parameter model, and neglect HOE for the simplification. Yes. So now we can replace this circuit with the approximate H parameter model. Yes. This is HIE and this one is HFE into IB. Yes. And here we are having the RC, and here we are having the capacitor, and this one is RL. Yes, at input side we are having the RB and RS, then source voltage. Yes, this is emitter, this is source voltage, this is source resistance RS, this is RB, and current flowing in this is IB, and this one is RC, this one is RL, this is CC. Voltage across this load is V0. Yes. So this is our approximate H parameter model. Yes. Now we can replace the current source. Here we are having current source as HFE into IB. Replace the current source HFE into IB with voltage source using transformation. Yes. So now we are having the current source as HFE into IB, and it has parallel resistance as RC. Yes, we can make it as voltage source by using the transformation. Yes, so now I am drawing only output side, so it is replaced with the equivalent voltage source, positive and negative. So we can write current into resistance, it is nothing but HFE into IB, it is nothing, HFE into IB into RC, it is nothing but our voltage source. Now this resistance become series. Now we are having this capacitor, coupling capacitor CC, and this is RL. Yes, this is RL. So now this is only output side. So input side is common. Yes. So here output across RL is named as V0. So when you are observing this part, the CC and RL forms the CR network. It is looking like high pass filter. It is high pass RC network. As this C and R network is acting as a high pass filter at low frequencies. So we can write this CC and RL form a network, form a high pass network, high pass RC network at low frequencies. At low frequencies. As this RC network will act as a high pass filter. That means if signal frequency is low, or decreases, then reactance of CC will be increases. When you are applying this signal, low frequency signal is applied, then reactance of the CC will be increases. As our Xc equals to 1 by j omega c, when frequency decreases, then Xc will be increases. As then voltage across CC will be increases. Voltage across CC will be increased. So when reactance increases, this drop across this capacitor also increases. Then voltage across RL will be decreases. Yes. So drop across CC increases, drop across RL will be decreases. Then we are taking it as a output V0. Then we can say output is decreases. Then we can say V0 by Vin is decreases. So gain is also decreases. Yes. So this CR networking as acting as a high pass filter. When you are applying the low frequency signal to this network, the reactance offered by this capacitance is increases. Yes. Then reactance is increases, then drop across this capacitor will be increases, then drop across this load resistor will be decreases. Then we can say V0 is decreases. Then we can say V0 by Vn will be decreases. Yes. Then we can say this coupling capacitor decreases the voltage gain of the RC coupled amplifier at low frequency. Yes. Simply we can say this coupling capacitor is decreasing the gain of the RC coupled amplifier at low frequency. Yes. Thus the coupling capacitor CC decreases the voltage gain of RC coupled CA amplifier at low frequencies. At low frequencies. Yes. So in general, voltage gain decreases at low frequency because of large capacitor. Yes. In general, voltage gain decreases at low frequency because of large capacitors. Yes. So we can draw the graph like this. This is frequency, this is voltage gain. So you will get these kind of output. Yes. So it is nothing but low frequencies. So this is mid frequency. So when it is moving from mid frequency to low frequency, the gain is decreases. Yes. If voltage gain V0 by Vin is calculated by including the effect of coupling capacitor. Yes. If V0 by Vin is calculated by including the effect of coupling capacitor, then it is called low frequency voltage gain. Then it is called low frequency voltage gain. Why we need to calculate the voltage gain again? Because at low frequencies voltage gain is decreases. Yes. So again we need to calculate the voltage gain at low frequencies. This is called low frequency voltage gain. So I am naming this one as AVL V0 by V in. It is equation number 1. Why I am writing L? Why? Because voltage gain at low frequencies we are calculating, it is equals to V0 by V in. So we can write equation number 1. Yes. So using voltage division at output circuit, what we can write? We can write V0 equals to minus HFE into IB S into RC by RL by RC plus RL plus reactance offered by our coupling capacitor is 1 by j omega cc. Yes. From this we can write V0 equals to minus HFE into IB into RC RL by taking the common as RC plus RL. So RC plus RL, then we'll get 1 plus 1 by j omega cc into RC plus RL. Yes. So can we write RC into RL by RC plus RL is nothing but it is a parallel combination of RC and RL. Yes. Parallel combination of RC and RL can be written as R dash L. So we can write V0 equals to minus HFE into IB by S. This combination we can write R dash L 1 plus 1 by j omega cc into RC plus RL. S. Here we replace the RC into RL by RC plus RL. So it's nothing but RC is parallel with RL. We can write it is equals to R dash L. Yes, that's why I have written R dash L here. Yes. So now it is equation number 2. From input circuit, what we can write? Vi equals to, from input circuit, Vi equals to, we can write IB into HIE. This is equation number 3. As V0 by Vi is nothing but equation 2 is divided by equation 3. Then we can write V0 by Vi is equals to IB and IB will be cancelled. We can write directly minus HFE into R dash L by S HIE into 1 by 1 plus 1 by j omega cc into RC plus RL. Yes. So here it is minus HFE into R dash L by HIE into 1 by 1 plus 1 by j omega cc into RC plus RL. Yes. Can you write this is a voltage gain? Yes or no? So can you write this is a voltage gain? So this is the voltage gain at mid-band frequencies. Yes or no? We already derived this one. So voltage gain minus HF into R dash L by HIE. So it is the voltage gain at mid-band frequencies. That's why I am writing it is AVM. Yes, we can write AVM. So from this we can write AVL equals to AVM into 1 by 1 minus, we can write 1 plus j omega. We can write it is 1 by 1 minus j omega s into, we can write 1 by RC plus RL into CC. Yes. So we can write this part. So this part is looking like, omega L. Why? Because omega L is nothing but 2 phi f. Yes, omega is nothing but 2 phi f. So we can write 1 by RC is nothing but omega L. Why I am writing here omega L equals to 2 phi f. F can be 2 phi FL. FL can be replaced with 1 by RC. Yes. So we can write this term as omega L. So we can write AVL equals to AVM by 1 minus j omega L by omega. Yes. So omega L by omega. Otherwise we can write omega equals to 2 phi FL, omega equals to 2 phi F. So we can write it is also equals to AVM by 1 minus FL by F. Yes, means J into FL by F. So from this we can write FL equals to what we can write 1 by 2 phi S CC into RC plus RL. Yes or no? Yes. So this is the voltage gain at low frequencies. It is equals to AVM by 1 minus j FL by F. Yes. What is FL? FL is nothing but lower cutoff frequency here. Yes. So now we will calculate the magnitude of this voltage gain. AVL equals to, magnitude of AVL equals to, we can write mod AVM by under root of 1 plus FL by F whole square. S, and we can write the angle at an angle of AVM equals to 180 degrees plus tan inverse of FL by F. S, that means 180 degrees is offered by the C amplifier. Now we are considering the effect of that coupling capacitor. So now AVM at an angle of AVM equals to 180 degrees plus tan inverse of FL by F. From this we can write S, because we know AVM is already 180 degrees. That's why we have written 180 degrees. S, because of AVM 180 degree, AVM is negative or 180 degrees offers. Negative means it offers the 180 degrees. Yes, that's why I am writing here this part. Yes. Now effect of this coupling capacitor is indicates the tan inverse of FL by F. If FL and F1 both are same, then we can write tan inverse of 1. The maximum phase shift offered by this RC network is 45 degrees. Yes. So at F equals to FL, we can write mod AVL equals to what we can write mod of AVM by root 2. Yes, here FL is nothing but lower cutoff frequency or lower 3 dB frequency of RC coupled C amplifier. That means This is the frequency versus gain, frequency response of RC coupled amplifier. Now I am assuming this is my frequency response of RC coupled amplifier. This is the gain S. So this is FL, this is FH. FL is nothing but lower cut-off frequency, FH is nothing but higher cut-off frequency. From this we can write bandwidth equals to FH minus FL. S, higher cut-off frequency minus lower cut-off frequency indicates the bandwidth. S. So simply we can say the CA amplifier is used at the audio frequency levels. That means below 20 kHz, 20 Hz to 20 kHz. S. So the bandwidth of the audio amplifier we can say simply it is about 20 kHz. S. This lower cutoff frequency is FL, higher cutoff frequency is FH. So in between the FH and FL to FH frequencies, the gain of the amplifier is audible. The gain of the amplifier is audible or useful. S. So at which frequency the gain of the at which frequency bands the gain of the amplifier is considered or useful, then it is called bandwidth. S. So this frequency is nothing but mid frequency. Mid frequencies. S. So here FL is nothing but lower cutoff frequency. Lower cutoff frequency. So before the lower cutoff frequency, the gain is decreases. The gain is decreases. So as an analog engineer, we are always choosing the higher gain. S, or at which frequency gain is constant, that is lower cutoff frequency. S. So lower cutoff frequency or lower 3 dB. So at which frequency at approximately 70% of gain is generated, that is called 3 dB frequency. S. So this is the effect of only one coupling capacitor is considered here. S. If there is bypass capacitor is considered, then if effect of bypass capacitor C is considered, then we can write FL2. So now we can say it is FL1. So now it is FL2. Then we can write GM by 25CE. As CE is what? Bypass capacitance. When it is applicable, if XCE is less than RE value, that means the reactance offered by the bypass capacitance is small compared to this emitter resistance. As we are always choosing this smaller reactance only. As next, if effect of blocking capacitor is considered, CB is considered, then we can write FL3. I am naming this one as FL3. It is equals to 1 by 25 CB into resistance is RS plus R dash I. RS plus R dash I. Yes, we already know R dash I is nothing but RB is parallel with HIE. Yes, in this way we can calculate the effect of each and every capacitor in the RC coupled CE amplifier at low frequencies. Yes. So this net FL is the highest above these three frequencies. So the net low frequency FL, lower cutoff frequency, is highest of these above three values. Here we are having FL1, this is FL2, this is FL3. That lower cutoff frequency, the net lower cutoff frequency must be highest of these above three values, is at least 4 times of the remaining two frequencies. Yes, so we can write net FL is the highest above three frequencies. It is greater by at least 4 times in comparison to the remaining two frequencies. As if you want to calculate the net lower cutoff frequency FL, then we can write approximately. We are writing approximately 1.1 into under root of FL1 square plus FL2 square plus FL3 square. This will be the net lower cutoff frequency by considering these three capacitors. Yes, these three capacitors. How it affects on the phase shift? We know our CA amplifier offers the 180 degree of phase shift. Now this coupling capacitor CC is also provides the 45 degrees of phase shift. As it is nothing but tan inverse of FL by F. When FL equals to F, tan inverse of 1 equals to 45 degrees. Yes, so you can write a note. This RC coupled CA amplifier provide phase shift of 225 degrees at low frequency at FL. Yes, it is nothing but 180 degrees plus 45 degrees, it is nothing but 225 degrees. Yes, at FL at lower cutoff frequency, it offers the 225 degrees of phase shift. Yes, so in this way, this blocking capacitor, coupling capacitor and bypass capacitors affects the RC coupled C amplifier. Yes, next we'll solve the problems on this topic. Thank you.